Welcome to the ISTS Distinguished Colloquium talk this evening by Professor Sarit Kraus from Bar-Ilan University. It's a very great pleasure for me to host her as one of the preeminent experts in AI in the world today. Sarit has won virtually every major AI award around, going back to the 90s when she won the IJCAI Computers and Thought Award, to the Emmett Prize from the President of Israel for her work in artificial intelligence. She's chairing the biggest AI conference of the year later this year. I'm sure a matter of both pride and regret. And so she's worked extensively over the years on reasoning multi-agent systems, autonomous systems where multiple agents cooperate to make intelligent decisions. She's one of the founders of the use of game theory in AI for many, many real-world problems, including patrolling problems, for which she received an award from the city of LA. So without further ado, I'll let Sarit tell us about her work today on machine learning applied to financial fraud.
Thank you, Ves, for your kind word, and thank you for coming. You know, online banking is increasing. I don't know if here, but in Israel, banks are just closing branches because everything goes online. And for example, this app, you know, we do all the transaction using this app now in Israel and everywhere. But as the amount of online banking increasing, the fraud is also increasing. And there are many challenges in finding fraud in online banking. The main problem is the imbalance. You know, there is one in many thousand transactions that is a fraud. But this one can cost the bank a lot of money. So this is one problem. Another problem is there is sparse data because every transaction has its own features and it's make it very difficult. There are multiple types of transactions. There are transactions involved in more than one bank, and then you don't have information about the other bank. And there are relative small number of annotated examples, and there are not much data per user. So that's why compare, for example, to credit cards. In credit cards fraud, there are many, many papers, a lot of models, and it's working since the 90s. On the other hand, on online banking and fraud in online banking, it's not common to have papers, research about doing this. So what do banks do about this problem? So usually they hired a third party who is providing them a service of identifying frauds. What these third parties are doing? So they have some machine learning models with many, many parameters of the, the app, the IP, the type of machine, the location, many, many features and parameters of the transactions. And then they have some machine learning model, and they don't tell the bank whether it's a fraud or not. They are giving the bank some risk score. And now the bank can do several things. Given the risk score, they can decide to allow putting the transaction through. They can deny it. You know, these are the two easy things. They can challenge, make the challenge to the user, I don't know, like asking his birth date or other authentication things, or calling the bank, or giving, users of banks, customers of banks don't like these authentications. Or they can be reviewed by a human expert, but this has delay, and also human experts are very costly. So given this score, risk score, the banks need to put thresholds over what are the four categories to apply, given the score. And the companies, the companies that provide the score, telling him what is the percentage that will be for transaction in each score. So they decide, maybe how many people they want to buzzer because of they worried, or just, if there are transactions, they make so much money. There will be transactions that is a fraud. They will pay back. So that's something to decide for the bank. Now, oops. Now the battery went. Okay, what should we do? We do this one. I will do that. Okay, now one important thing to say is that given the risk score, one of the things that the banks would like to get explanations. Why this risk score? Why? So they can make better decision on also retroactive. If I deny the access or the transaction, customers want to know why you did it to us. So explanation plays important role here. So what does this company, the third component, that provides the service, what do they do? So they get data from the bank and data that are annotated. Some are annotated as fraud and others are not annotated at all. That means usually they are okay, they are not fraud. But in order to give the service, they need annotated examples. And then they are doing some machine learning models, and then they have some work. The problem with this is that the available data is limited. Why? Because the banks don't really like to give data to somebody, even if they are on their side. So that's one problem. The data there's fixed procedures, so the data is very problematic. And as I said, there are poor history of a user, because think about it, how many credit card transactions you have in a day and how many transactions you have. So there are some, I saw the data, there are some customers that have many transactions, but most of us, how many transactions do we have in a bank in a day? I mean, in a week, in a month, think about yourself, and you realize that this is not that common. You don't have many transactions. So in this talk, I would like to tell you about our adventures that we have in helping such search company, some company that provide this service. And the first part will be about attention-based neural network for detection of online banking transactions. And the second part of the talk will be about transfer learning from one bank to another. And then if I have time, I'll tell you about really different work that I'm doing about physical security. Okay, so let's start. So one of the things that when we came to this company, that we realized that frauds are usually is not one transaction. In order to perform a fraud in a bank, you need to do a few transactions. That is, you log in, you are looking at the things, you are then eventually you move money, that's your goal, and then you log out. So in essentially, the fraud is based on sequence. However, unfortunately, major current approaches, they are just looking at one sequence, one transaction at a time, not on sequences. The best algorithms, the best approaches, what they are doing, they do all sorts of averages. What is the average number of times that this user uses IP? What's the average number of times he perform in a month that he move money, pay money? So they are looking, but they didn't look at sequences. And we decided that sequences should play an important role in finding fraud. However, managing sequences is not easy. So there are two ideas that we have in mind. Thinking about machine learning and sequences, everybody told us use LSTM networks. You know, we have friends in natural language in Bar-Ilan. They say, LSTM, this is the way to solve your sequence problems. On the other hand, there was other friends that said, no, no, no. You should use attention mechanism. Attention mechanism allow you in a sequence to give different weight to element in the sequence, but they are simple. They are easy to implement, easy to train, use these things. So we have these two approaches, and we decided to look at them. And the idea was, why won't we do hierarchical form of attentions? We have two issues here. Each transaction has features, and we can think of a different attention of features in different situations. So this is one. And then the other thing is we have the entire sequence, and we can give different weights to different transactions in the sequence. So why won't we use attention on both levels? So this is the idea. And the most important issue of the attention is that it gives weights both to features and to transactions in the sequence. Then we can explain, why did you think that this is a fraud? Because this feature got higher attention, or this transaction got higher attention, and this will be useful for explaining the why this activity was, this sequence was a fraud. So we got data, real data, from one of the industry-leading fraud detection companies. The data is being sent to the vendor from the bank, and it was fixed and predefined way. So we have transactions, which is a set of features, and then we have a sequence, which are a set of transactions. So that what we are having. And we had three main components of the system. One, we had to handle the features, the values of the feature. Why? Because these features were discrete and very sparse. So we had to somehow make the representation more compact. And then we move them from a discrete case to some dense feature representation. So we had to learn how to do that. Second, we want to do attention over features. We had to learn this aspect as well. And finally, we want to do attention over the transactions. So this is how it looks, the algorithm. But if we look more locally, you can say that first we have to do some feature embedding. And intuitively, we are multiplying the features with a matrix. Because feature representation was sparse, we have discrete value. You have a vector where each possible value appears as a bit. So we are creating a feature embedding. Then we are computing weights for each feature using this function. This function over the embedded features with weight, and of course normalizing it. And then we are eventually have a value associated with each feature. Once we have this, we can move with each transaction. Once we have this, we can move to the sequence. Then we can compute the value of a given transaction. What do we think locally, whether this is a fraud or not? Then we need to give weight for each of the transactions. And then we can have some sort of weighted averaging of the local decisions. So this is the step of the process. And my student decided that there are many things to learn there, the function of the features. So he decided that he put one network and learned everything at once. when students succeed, I don't complain. And so he had, I think, enough data. And OK, so how did we get the data? So we have 6 months of data from 2017 belonging to some South American bank. We have 80 million transactions, out of which only 22,000 were marked as fraud. The others weren't marked. So actually, you are not sure if the others are fraud or not, but we assume they are not fraud. Most features were categorized by nature, like IP, like whether the, also male or female, all sorts of features like this. But non-categorical features, such as payments, which is a very important feature, were also discretized. Then we added also user identifier. We have missing values, a lot of missing values about this data. It's very noisy data. So we clean it, not me, the student. OK, then he did undersample of the data because there was so many transactions and only 22,000. So we kept all the 22,000 fraud and sampled the other data because otherwise he couldn't manage it. And we decided that the sequence, after doing all sorts of analysis, that the sequence will be 7 days prior to a transaction. So we have a transaction, we take all the transaction in the previous 7 days, and this is a sequence. So think about it, sequences were of different lengths because there are some users that have many activities in the 7 days and others that not. So this makes it more difficult. And we also, at the end, we ended up with 57 features for each transaction. Life is not easy, what can I say? And so you can see this is an example of a fraudulent sequence. This malicious person did a login, he views a statement, he then did a login again, then he made eventually a payment. This is their goal, to make the payment to some place and run with the money. So we decided to compare various methods. So our method is here, feature and sequence attention. This is what we propose, that you have attention of both the features and the sequence, but we compare with only attention of the features, only attention of the sequence. Decaying weight, that is, we have attention of the feature, and then on the element of the sequence, we have some weights that was decaying as you went earlier in time. We have what the company was doing now, only looking at the last transactions, and we did attention of the features, and then we use LSTMs as a comparison. So here is the most interesting results. So, we are doing a false positive, false negative. You need to decide what do you prefer, to buzzer people because you told about good transactions that it's fraud, or you can lose money, but how many fraud transactions you really found. So this is a trade-off. And of course, if I will always say that a transaction is a fraud, there will never be a fraud transaction that will, but then I'll buzzer all the, The banks want the transaction to go through because they're making money on these transactions. And they're losing money on fraud, so they need to balance. So you can see, interestingly, that the ones that did attention both on the features and the sequence got the highest AC. And then you can see the ones that did, we have the sequence and then the LSTMs. These are the top sequences, these are the 3, that has to do with the top methods that has to do with sequence did the best. And of course, ours was the top, that's why I'm here. And, but it was very interesting because we wanted to convince the the vendor, you need to look at sequences. Stop looking just on local transactions. So this was a good proof to this. And as we are noticing, it's better to have attention on both the features and the sequence. So sequences are good, attention on both things are also good. Here you can see how much money we saved to the bank by using each of the, and here this is where the bank put the threshold. You know, as you are going up, you are saving more money. As you are wasting the time of more customers, you are saving more money. Usually they putting here, and that you can save 80% of the loss. So you're looking at the money, how much money they will lose if they are not saying this is a fraud. And these methods can, but you can see that also the LSTM, this is the yellow one, was doing quite well at the beginning, but as the bank put more, allow more to bother more customers, our methods did better. But again, sequences are better than non-sequences methods. So then we wanted to see whether attention really helps, and whether they make any difference, whether they have different. So we looked what was the feature, the sequence with the highest attention, with the highest weight. And we normalized it. So if there was at the, as close the one that the last one, then it got a weight, it was here. If it was far away from the transactions that we want to look at, it was here. But you can see, while they are quite similar, you can see that genius, you know, the good transactions, in the sequence, they look at the ones that we are considering, but less in the bad ones. Because in the bad one, usually the activities that lead to the ones that they can identify as leading to the fraud appear earlier. And to do this, we actually print out weights of transactions and sequences. So you can see here, do you see here? No, wait, I can do this. Okay. Okay, so you can look here. These are the transactions. So the ones that we want to decide whether it's a fraud or not, it's here. And these are the area ones. So we look here at 10 transactions in a sequence. And these weights say what are the transactions that got the highest weight. So this is the same user. This one was a fraud sequence, and this one was a genius, a good transactions. And this one was a fraud. This is a second user. So interestingly, you can see, can you see it? No. I thought you can see the pen. You can't see it? Okay. So I will point. How should I do this? Okay, I will try. So you see, these ones are for the sequences, and these are the features. I told you we have 54 features, and these are the weights. So this is a good transaction. And you see the weights that got the highest was the ones that we tried to figure out whether it is a fraud or not. And also here. Here, the difficult transaction wasn't the last one, but two in advance and previous to that. And we looked at it, and it's turned out that the one over there, it was because it was very close to the sixth one, and also this one missed answering some authentication questions, and this has to do something with login. And here, it was enough to look at the correct one. And also, you can see of the features that you get different weights over features for different, whether it's true or not, and so it's very specialized. And you look here, you can explain to the expert, or you can generate explanation why this kind of transaction was classified as fraud or classified as not fraud. So this is very useful to have these weights. This is an example. We can look at other ones. OK, so just to conclude about this first thing, we saw that modeling online betting fraud detection problem as a sequence classification is beneficial, and this is really useful. We developed online classifiers that apply attention over feature and over sequences. This leads to ability to provide explanations, and also it's really easy to train. And so the model is simple, is powerful, and we hope that we will be able to convince this vendor to use it, which is probably the most difficult task in the project, because they are very conservative and take the time to adapt. And banks also very conservative. But we show them that this is really working. OK, but you notice that all this work depends on the bank providing you with some information about transactions that are fraud. Without that, you can't do much. How can I learn without data? And the problem is that each time this company has new bank, for 3 months, they just need to wait that there will be experts that will annotate data, that will say this is fraud, this is not fraud, and et cetera. And another problem is that there are some banks that are not cooperative. They don't like to spend the effort on annotating data, et cetera. So these banks make our vendor very unhappy, because what can they do? They don't know if it is a fraud or not. So what we propose to them is to do transfer learning, is to use data from a few banks that they have good data on them as a way to do prediction on banks that are new or don't have a good annotation system. So that was the second task of this project. And the idea is what we have a transfer, we have features source with fraud or not fraud annotation, and then we have features of the target. In transfer learning, you have a source and a target. You want to learn from the source into the target domain. And here we have this is the source and this is the target. And the question is, can we do that? That was the question. So our idea was, one interesting thing in this domain, in these banks, so the bank has many, many transactions. No problem about this. They are willing to give, even new banks can look at the last 3 months and give 100,000 of transactions. That's no problem. The only problem is that they are not annotated. So you are taking the good guys, the data from the banks that are annotated, and you are taking featured, many, many targets, transaction with features of the new bank, and you want to take these transactions and annotate them. That was our idea. Let's annotate these new transactions not based on the distribution of the features. How we do that? So once we have this, we'll have annotated data, we'll put it into the machine learning algorithm, and we have a machine learning model. And the idea is that as this bank will collect more data, we will be able to improve the machine learning algorithm. So our idea was the following. Giving a set of all banks and one new bank, what should we do? We first need to compute the similarity between the new bank and the old bank. Based on what? Not on the annotated data, about their feature distribution. How similar these two banks are. I don't know if you know that banks are very different. There are banks for military, there are banks for government, there are banks for in rural situation, in agriculture areas. There are different banks provide different, so we are looking at the features and not on the annotation, and look whether they are similar. Then, for each old bank, we are computing risk score of the transaction of the new bank, and using the model of the old bank. So you have the features, you are putting the feature of the new bank inside the model of the old bank, and you get a score value, risk score value. Then you compute some weighted sum based on the similarity times the risk score. So you have 10 banks and you have a new bank. So each of the 10 banks, you are computing about each transaction, what is the risk value that it will compute, and then you are doing some weighted sum. And then you use the annotated data to build the model of the new bank and improve over time. So the only problem in this is how you do similarity between banks. We are talking about discrete values. It's not, you can't use any continuous similarity. So what we decided to do is to build histograms for each feature and normalize them to sum to 1. So we take a feature, we have 100,000 of transactions. We are, for each value, possible value of the feature, we are counting how many times it appeared. And then we have, for each feature, we have histograms on the possible values of this feature. Now, we are using, for each feature, we can look at a similar feature of the old bank, new bank, old bank, and compare between the histograms. All of them are normalized. Then we tried various things, and eventually we decided to use intersection kernel to compute similarity between the histograms. You can find it here, and then we get a number between 0 and 1 for similarity over features between the old bank and the new bank. Okay, but this is just for features. Now I want to know about the entire set of features. So how will we combine a similarity of every feature for similarity of banks? Then we use neural networks to return similarity between banks using the data that we have. So this was the similarity computation. Once we have this, we could run experiments. We had 3 months of transactions of 11 banks, which are labeled and either it's fraud or not fraud. And we always use one left out. So we assume first bank is a new and the other 10 are old. And for new bank, we left some validation data that was marked as fraud or not. And we removed, of course, the labels of the training data, and we use all these procedures.
So the accuracy, what metric was used?
Okay, so this is a good point. What we just compared is we compared what on the validation, what is the validation was marked whether it is fraud or not, and the annotation, the new annotation, I'm just saying the 90% accuracy is on the annotation of the data that we are going to use later as a prediction. So this was 90%, whether we are correct or not in the annotations that we gave compared to the actual annotation that was.
But if the data is imbalanced, this would not be.
Yeah, but for the validation, we took a balanced set, because otherwise I need to do AUC. But for the validation, we took balance there, which is fair enough. OK, so again, we were very happy with these results. And we hope that the vendor will start working with this method on their new banks. So this was about banks and finding fraud. And in the next 10 minutes, I think, I will use 15 minutes, I want to talk a little bit about actual physical security and some robots, So let me tell you about this project. So today there are a lot of autonomous vehicles, like UAVs, like robots going around. The problem is that currently on a UAV, expensive UAV, there is not only one person taking care of it, there are sometimes 2 or 3 people. And drones, maybe they put one person on two drones. And this is some robots. They usually put one person on one robot. And our goal was, this is a small robot moving around. So these are, as you can see, are autonomous robots. They can move around. They are looking for, they cost $1,500, very cheap robots. They can move around and find whatever you want them to find. So the question is, if they are autonomous, why do I need people in the loop? Why all these autonomous robots, drones, etc. have people? So there are 3 reasons. What are the people are doing there? So one, these robots are getting into trouble, and sometimes they are broke, and if it's really important tasks, they want a person to fix things when something goes wrong with the robot. OK, I can understand that. Then there are tasks that people are doing better than the robot by themselves. So for example, these robots tend to get into the ladies' room in my lab, and they are getting into some places, and then, they're autonomous. Eventually, they will be able to go out, but if there is a person coming, not me, but one of the students coming and driving them, they can driving out much faster than the autonomous robot. And also like pictures. So eventually, the robot can identify what's going on, but people are sometimes much better. So this is the second. And the most important thing why there are people in the loop in all these robots, because our customers don't like to give the autonomy of robot to making all sorts of decisions. Well, one thing is shooting. No one wants the robot to shoot without an approval of a person. But also in health, they want the person to make sure what's going on. So this is that there is still not enough trust in the autonomy of the robot. Same in autonomous cars. It's not the ability, it's the trust in the system. OK, so now the problem is this guy has these 10 robots going around, 20 robots going around, and he needs to get involved. So people are overwhelmed by this request. So all the time come requests from the robots, and it turned out that experiment shows that people can manage 5 robots. Of course, it depends how autonomous are the robots, etc. But so we got this project, and they told us, what can you do that one person, very cheap robots, so these robots need help from people, and one person will be able to manage more than 10 robots. OK, I said, OK, let's go for it. And what we decided that what this person really needs, the person needs an agent that will help him. And the agent will help the team. So I see it as a person, the robot, and the agent helps the team by processing noisy signals, by prioritizing tasks for the person. The main thing that he's telling the person, the agent telling the person what to do, now do this. So there are all these requests coming, and he prioritizes these request and tell the person what to do. This is really helpful for people. And how we did this prioritization is based on data that we collected, and the data is both on the person and on the robots. And we both brought 10 people to the lab, 30 people to the lab in order to collect data on people. And we also ran many, many simulations with robots. This is much easier than people. And based on this, we built a classifier that ranks the task of that arriving from the robot and tells the person what to do. And okay, does this really help? Does the agent really help the people? And the question is, yes. We ran both experiments with simulation with people, but also we brought 12 people to the lab with the real robots. And we tell them what the robot did. The robot looked for green balls in the lab. And the question was, in a given time period, how many balls the person with the robot can find together. And six people first did the task with the agent and the robot, and then without the agent, and six did the other way around. So it was really a control system, and what we found out. So without the agent, the team found on average, seven green balls. At the same time, with the agent, they find 14 on average. But it wasn't just on average. Every of the 12 people that was with the agent, the team found more balls than without it. And you can come and play with it. You'll notice it's really, really helpful. And we ran experiments with this, and we ran experiments also in simulation of small storage. Everywhere, the agent is really helpful for the people, I'll say for the team to reach its goal. So based on this, my student developed
Dispatch?
Quick! There's a student missing in the northern section of the campus.
Give me the exact location. A unit is on its way.
In disaster environments, both the victims' and the rescuers' lives may be in danger. Robot technology can provide solutions. Today's robots are semi-autonomous and require a human operator's help whenever they cannot handle the situation on their own.
Move Agent 3 away from Agent 4. Move Agent 4 away from Agent 5. Manually drive Robot 6 to a better...
The fast-paced, simultaneous streams of data from multiple robots can be overwhelming and can be a grueling task for a single operator.
Your robots are too close together. Spread them around. Your robots are too close together. Spread them around. Manually drive Robot 6 to a better position. Move Agent 3 away from Agent 4.
Here in Bar-Ilan University, we have developed an intelligent agent that supports the human multi-robot team collaboration. The agent prioritizes the different tasks, filters the robot's signals, and generates warnings which enhance the operator's situation awareness, thereby allowing him to make better decisions. The agent uses a novel methodology combining machine learning and optimization techniques, which accounts for both the operator's abilities and the robot's performance in real time. Through extensive empirical evaluations, we have shown that our agent was able to significantly enhance the team's performance, which can translate into saving lives.
There he is. We found him. We got him. I'm sending you the exact location now. Dispatch out.
So this video won ISTS a competition on a video on robots, and you can guess why. I must tell you, when the student asked me to make a video for the competition, I said, come on. Why are you wasting my time? But they said yes, and now I'm using the video all the time. So the rule is, do whatever your student asks you, just do it. Okay, so now the question is, do you want to talk about the set, or do we, about patrols?
Well, I think we have another 5 minutes.
Okay, so let me just tell you about another project has to do with these robots, and this is about adversarial patrolling. And you can think about various scenarios where robots can be used for patrol across a round area, on a border, you can name it. And the question is, given a team of robots, how should they plan their patrols pass a long time to optimize some objective function? The choice should depend on the different robotic models and the existence of adversary and the environment constraints. So we are thinking all this work has to do with limited resources about to prevent, why won't I tell you a story? Explaining why I started working about this project. So I have a son, and he was working on some patrols across around a village, and that's what he was doing. They were doing security of some village, and one day he's calling me and telling me, "Mommy, they stole the horses." I said, "Avi, what are you talking about?" So he said, we were patrolling around, and the thieves waited till we were some place. They knew we will be there. They entered in, took the horses, beautiful horses, and ran away with them. So I told him, "Avi, you need our algorithms." And the algorithm is especially to this case about smart adversaries that learn your pattern and then use this information to get in and to get out and to take what they want. So how can you do this? What you need to do is to use randomization. So the adversary will not know, in the best case, what Avi could do, they could put guards all over the village, but it's too expensive. So instead of putting guards everywhere, you need to randomize the activity of the guards. In our case, are robots that are patrolling some place. You need to add randomizations. And we are looking about robots that are either moving across some closed polygon or some fence which is open. But fence is more difficult. And the task is not to prevent in 100%. We can't do that. It's just to increase, to maximize the detection probability. And that's the idea. So if you can see, there is some robots moving around. They are K robots. They are moving one section at a unit time. And the most important thing is the robot is here. Should they turn around or should they continue in the way they are going? And the probability is associated whether they will continue on their directions or they turn around and go to the other side. And this probability is characterization of their strategy. So this is what I'm telling you. So previous work was mainly focusing about uniform probability around everywhere. And this is, if everything is symmetric, that's what you want me to do. So you compute one probability, and in every time unit, the robot with probability P continue in one direction, and probability 1 minus P is going to the other directions. But it's not always possible, and it's not always the best way to do. Because if there are places where it's not symmetric, where the fence is higher or lower, and the adversary can get faster in one place and slower in other place, you need to find different probabilities to different. And this work was about this, how you are finding probabilities that are not equal, and this raises a lot of complexity problem. And so what we did in this work, in asymmetric situation, we show, you can see here, what if you, in previous work, they said you use uniform P. We are suggesting to use non-uniform T. And you can see in all the cases that we looked, and different kind of the times that the adversary can get in, the number of robots, the number, you can see that it is better to use non-uniform probability. And similarly, so that was the contribution of this work. So first, remember, it's good to have a probabilistic movement. It's good to have different probability in each location. And actually, you can think about it in a fence. Intuitively, the probabilities are different because when a robot gets to the end of the fence, with probability 1, he needs to turn around. So again, you need to think about all this problem with different probabilities. And again, we show that regardless of the problems, using different probability in each segment of the fence lead to higher probability of detection. And so this is another project I wanted to tell you. It's getting more interesting when you have multiple robots, and the question is, should they overlap? And again, we show that overlapping is always good. You can see over here. And I want to just conclude and mention that this is another work about randomization of patrolling. It's beneficial in complex asymmetric settings, and non-uniform strategies are necessary for preventing penetration. So I'll take question now.
So please join me in thanking Sarit for a very interesting talk. And I'll throw the floor open to questions.
My question is about the transfer learning part.
Yeah, okay.
So you mentioned that for a new bank, you compute the feature as the similarity of the new bank and like, let's say 10 old banks, right? So if I understand correct, you are kind of choosing which old bank model is like more similar to the new bank, no?
No, I'm taking all the 10 banks. I'm computing similarity for the new bank for all the 10. And then I'm computing what each of these banks will say about this transaction. And then I'm doing weighted sum between the similarity. Think about it like collaborative filtering. In collaborative filtering, what you are doing, you are computing the weight for several people, and then you are making the recommendation based on this weighted sum of the all banks. So I'm not choosing just the bank with a high similarity, but I'm doing weighted sum.
Yeah, so when you have the weights, are you applying the weights over the predictions of the old banks, or you're applying that over the features or something?
I'm computing the similarities
Yeah.
based on the features.
Yeah.
And then I'm using these similarity measures because for the old bank and the new banks, the things that I have are the features values. For the new bank, I don't have any annotated data.
Yeah.
So I'm using the features to compute the similarity, and then I'm using the prediction of the new banks on the transaction of the prediction of the old bank on the transaction of the new banks.
Yeah.
And then I'm doing weighted sum of
Okay.
this.
Okay. I got the point. Thanks.
Good question.
In that same vein, you said you used a neural network to identify the similarity scores. I just am curious what data you used.
No, so I'm using this measure of similarities, a kernel-based. This is not neural network. This is just computation. I'm taking this is a well-known similarity measure between histograms. So I'm generating histograms from the data of the old banks and the new banks. And then I'm doing similarity between histograms. But this similarity is just on each feature. Now I need to combine the similarity of the features to similarity between the banks. Here I'm using neural networks.
Yeah, so what would be your ground truth there?
Okay, so I know I'm putting data aside. So I'm taking just the 10 banks. On the 10 banks that I already know, I know how similar they are with respect to the prediction. So I use this as a ground truth and so now I'm having 10 banks. I'm leaving 1 bank away, and I can do this similarity.
Hi, Professor. I'm Chen. Thanks for sharing. I have 2 questions. The first is that we also know that there are a lot of third-party companies also doing such a kind of thing to prevent the fraud. Just like PayPal or the other companies, have you ever, understand what the models or what the algorithm or what the technology the company use, and have you ever compared with yours with theirs?
I can compare just with people that let me know what they are doing. So we could compare with the vendors that gave us the data. They had their system. And I don't know if you noticed, they were using, they have a lot of hard-coded features that they built over the years. And this is really excellent features. So they had a lot of features, and then they used some relatively simple machine learning model to them. What we were saying, didn't oppose what they are doing, because they are expert in their features. We said 2 things. One, you have a set of features, your features are great, Use sequences rather than focusing on just inventing features about because they are doing all sorts of averaging. So fine, use these features, but then take sequences into consideration. And then if you use sequences and you use attention both on the sequence and the features, you can have 2 things. One, you will improve your prediction. That's one thing. And the second thing, you'll be able to give explanations. So this is a win-win for them. So we are suggesting our method on top of the existing ones. We are not going against them. And then on transfer learning, of course, whatever method you are using, we are not getting into it. We are just telling you how to annotate new data, and then use whatever method you are happy to use. We are not criticizing anyone. We are just saying, on top of what you are doing, you can use what we developed. So this was the first question. What was the second?
The second is that I also know that the other kind of, fraud is like the check fraud. Check, the banking check.
Yeah.
For the scammers, maybe they just forge the signature and they forge the amount of the check and then deposit to the bank. Have you ever considered to solve this?
We didn't look at that, but notice that checks are disappearing. I know it's not in the US, but in Israel, No one uses checks anymore
Okay.
because they do online transactions. I know in the States there are still evidence, but I don't think I use any, because we have these apps. That, so if I want to give money for the private teacher of my kids, I just move it in an app. And if they don't want to pay taxes, they want cash. But anyway, they won't take. They won't take. Yeah, but this is a different question.
Thank you.
Thank you for the talk. I'm very interested in the semi-autonomous multi-robots that project. I'm interested in the question: what is the difference? What are the differences between like a centralized agent which controls all the different robots and the human in the loop control? So what are the two differences?
Yeah. Okay. So the agent is not controlling the robots. The agent currently is helping the person, okay? The robots, the idea is even if I don't care if the robots are managed locally. In our robots, they were autonomous in the sense that there was no central control. But even if there is a central controller of all the robots, there is still a person in the loop because of the three reasons that I told you. So the agent goal is to help the person manage this. And the video demonstrated why the agent is so helpful. Yeah. And you can come and try it.
Yeah, okay.
Okay?
And I also like the idea of explainable, you can explain the different ways of different transactions and features. I mean, is there any other, because you're using attention, it's naturally, we can see the weights of different components. I mean, are there any other classifiers that have such good advantage of being explainable?
Well, we did explanation. I can say only what I did, and I tried any help. We did a similar project about dating web page, where we wanted, it was recommending people who to approach, and we use a collaborative. It was two-sided collaborative filtering. So collaborative filtering also is a good source of explanations. Compared to neural network, that it's very difficult to explain anything.
Right.
So it depends on the domain. In our case, it works nicely. I
see. Thank you.
Let's take one last question and let Sarit off the hook after that.
Yeah, so you talked about looking at the sequences in the bank fraud example. And so what is the intuitive reason, what is the intuitive meaning behind a fraudulent sequence and a non-fraudulent sequence? I think there was a slide where you showed a fraudulent one, but I wasn't able to pick up why that was.
Okay, so I'm a fraud person, I'm the bad guy. So so my goal is to transfer money from your account to some, it's usually not to my account, to some third account that then will be transferred to my account, okay? So it's not just I am moving the money. I need to log into the system. I need to find out what, so this is for, at least I need to log in and then to do the transaction. This is one. So there are two actions, but usually it's more like this. Usually what I'm doing, I'm trying to log into the system, I'm changing the password, or I'm changing the authentication. And then this could be a few days earlier. And then I'm log in. And then the bank asks me for authentication, but I changed it already so I can do it. And then I'm moving the money. Another case, I can, a week in advance, I can log in and view your how much money you have in order to learn when you'll have money in the account. By the way, most of the frauds, they are moving small amounts of money. Then people usually don't notice. Just that, But that's the way the sequence. You need to do various things in order to eventually steal the money. So this is the sequence.
All right, just very quick.
It's just a tiny question. It was just following on that because if you can hear me, right?
Yeah.
If you are an adversary in this case, and your approach is to take a small amount of money, do I really need to check? Most people probably have $20 in their account, so I just take $20.
Yeah. Okay. So this was an example of action, but I saw in fraud transactions that they are logging. I don't know why they are doing it. They are looking at the statement. One of the reasons, okay, I can also think about why they are doing it, looking at the accounts and doing all sorts. Because one of the features are the IP where you are doing the activities. And the raising suspicious are when usually I'm using one IP and then there is, or usually I use a Android and then I'm logging from another company, with iPhone, okay? So one of the reasons they may do it is to make the system used to them being in the system. You see, before doing this thing. Because if you are logging and you are not moving money, usually you won't be indicated as fraud. So then the algorithm that is looking for different kind of activity is getting, because you are having these features of average number of times you used, I don't know, Android to log in the system. So, but I don't know, that's what they are doing now.
So just to be sure, I mean, it sounds like, following up on your questions, it sounds like this is identifying fraud in situations where an account has already been compromised, but you don't know that it's been compromised.
Yeah, that's it. Or the sequence give you some, just the person log in and immediately moves. There are all sorts of strange behavior about fraud. Otherwise, we wouldn't be able to.
And the other question is the following. So, so lots of banking apps on various mobile phone devices. There are some which are specific to a bank, but there are others that actually act more like gateways to multiple vendors or multiple banks. And so in your code, let's say it's used, where is it going to reside? Is it going to be in-app, which would allow us to have greater control over what's happening between multiple banks, or is it going to reside on the servers?
Currently, each company is working, each vendor is working for a specific bank. I assume the apps, and in Israel, for example, apps is owned by a specific bank, and they want to give services to all other banks' customers. That's why they make the money. So then the security is of the banks that give the service. But, as already now, banks don't like to cooperate, but there are some cooperation about IP, suspicious IP, and one of the things that if they will put all their data together, it's better. That's what we are saying.
All right, well, I've already exceeded the number of questions I promised to be asked by a fair margin, so please join me again in thanking Sarit.